an example. This was some floating point math blocks that we built a few years ago. And basically we made a floating point adder up here, so it's IEEE standard 754 floating point. This is a multiplier, this is an adder. This is a set of constants stored down here. There's some control logic over here. And what this basically does is polynomial evaluation. And you can compute polynomials by doing repeated add and multiplies without actually exponentiating, just like the BACS polyf instruction. And I loaded up the constants with the Taylor series expansion for e to the x and seeded it with an initial value of 1. And so when this circuit runs, what it does is it computes the value of e. And just to kind of give you an idea of what it looks like, this is a window into the simulated cell matrix. And the bright green squares show that there is at least one output that's being asserted. And the first iteration through this loop, I kind of ran it slowly to let you get an idea of what it's doing. And then I run it at more full speed with the remaining iterations. And you just kind of see how the data flows through there, and everything goes in an unclocked way. I have that video on my YouTube site with some techno music in the background, and it's gotten more hits than like all my other videos combined. Okay, so you can take normal circuits and you can map them onto your matrix, but you can also start thinking about other ways to use the cell matrix. For example, for massive parallelism. So say you wanted to simulate the behavior of a 3D volume of gas. It's a very complex computational question. But the actual computations you have to do to simulate one molecule are relatively simple. The question is that there's just so many molecules in a small volume. So what if you took a bunch of cell matrices and composed a processor to simulate each molecule? And in parallel, you could update the state of each molecule's position, its velocity, and so on. And then you can do a very efficient simulation. And so you can start thinking about cell matrix in terms of parallelism. You can also do search problems with this. For example, if you wanted to search through some large set of data to find a number that has some certain property, normally you search one number at a time. You take your first number, test it, take your second one, test it, and so on. Why not just build a huge number of processors, each one testing one number, and do all the tests in parallel? And so, as sort of a demonstration of that a few years ago, we went after the problem of cracking DES encrypted text. So, if you have a piece of plain text and you have a piece of ciphertext and you know the encryption algorithm, how do you find out what the magic key was? Well, the easiest way is just take all the possible keys, see which ones turn your plain text into your ciphertext. So we did that. We didn't have enough hardware to do 56-bit DES, so we made a 4-bit version of DES. We've got 16 keys, and we just did exactly this. We built 16 processors. We fed the plain text and ciphertext in, and then each of these tested an individual number, each testing its own key. And after they run through the DES loops, the final answer gets dribbled back out up into the upper right corner, and it was able to actually guess what the key was that we started with. Okay, so what's going on here? What you're doing is you're taking space and you're trading it off for time. You're taking problems that are very time intensive and saying, let's do them in a reasonable amount of time and make them very space intensive. And the idea is basically, if you have enough money or resource, you can buy more space, you can buy more hardware, you can never buy more time. You can't say, I'm rich, so I'm going to, have 500 years to solve this problem. If you need to know the answer in 5 minutes because your satellite is about to crash into a planet, and you need to get another navigation system running, right? So trading off time for space. And also starting to get into this idea of one machine, one problem, where instead of having fixed hardware, you modify the hardware based on the problem you're trying to solve. If you're doing a lot of floating point arithmetic, you build a bunch of floating point units. If you're doing string processing, you save that hardware and you use it to build some string processors. And maybe this changes over the course of your algorithm execution. So you're starting to think about sort of these kinds of ideas as opposed to having a fixed hardware platform and just running an algorithm that's been written for it. And the key to doing this is 10 years ago I would have said it's nanotechnology, but nanotechnology has been kind of usurped as a marketing term now. So we prefer the term Zeta technology. Art Drexler is using this term. Nanotechnology is basically focused on making things very small, okay, nanometer scale. My laptop uses nanotechnology because the transistors have 90 nanometer feature size, right? So nanotechnology is good. We're really interested in making things numerous. So Zeta technology, 10 to the 21st, trying to put a large number of things in a small area. And it's actually harder because first you have to do the nanotechnology to make things small, and then you have to make them numerous and dense. So you sort of got to do the first one and then do the second one. That's what we're really looking for, though, is moving into a realm where we have this kind of fabrication technology available. And is it feasible? Well, if you take a block of carbon about 1 meter on a side, and you do the chemistry calculations, you find it contains about 10 to the 29th carbon atoms. And if you look at some of the mechanical switching ideas that are out there, just for the sake of argument, let's say you can take 100 carbon atoms and build a switch out of it, an AND gate, an inverter, something like that. And you need 1,000 switches to make a cell. That one block of carbon could hold about a trillion cell matrix cells. So an Avogadro scale processor is being close to Avogadro's number. That's sort of what we're thinking of. Okay, so not 1 million or 1 billion cells, but something closer to a trillion. And we don't know the chemistry to make this happen yet. But we're sort of working with the architecture under the assumption that at some point, nanotechnology, data technology is going to get to the point where we can suddenly manufacture these huge numbers of cells. And what are we going to do with them at that point? That's sort of where the interest is right now. And you should be pretty skeptical at this point, right? Because everything I'm saying might sound good, but there's a whole bunch of details that I skipped over, okay? Very basic details. For example, bootstrapping a system. If you have a trillion cells and it takes you only a picosecond to bootstrap each one, it's going to take you 10 to the 12 seconds, which is about 32,000 years. Okay, it's just to configure your system to boot it up. So that's a problem. There's the question of faults. So a Pentium with 1 billion devices, let's say it can run a year before you get sort of a random upset in there. Well, if that scales up to a trillion devices, your mean time between failure goes from a year down to 32 nanoseconds. So every second you're going to have about 31 million upsets in your system. And you're not going to be able to ignore those anymore. You're not going to be able to use something like a parity check. You're going to have to do something much more creative in terms of actually dealing with these defects and correcting them and living with them. So that's an issue. And more generally, the whole question of how to manage the system at runtime when it has that many components, how do you look for events, how do you respond to events, is just a huge problem.
Are there any uncertainty, quantum physics uncertainty questions that arise?
I suspect there probably will be if we actually get to a point where you can build a feasible Avogadro scale system. You're probably going to be getting into all kinds of interesting failure modes, or modes where something might be going wrong and you're not sure, or where one thing's affecting something else in a way that you didn't expect. I mean, the physics is getting really weird already. And probably at that scale, yeah, there's going to be lots of new challenges.
You call it a failure mode in that case. It could almost be normal,
yeah,
undetermined.
Yeah. And there's actually some ideas out there for how you can take advantage of that to do some things, especially when you get into applications related to like evolvability and genetic algorithms where you want to introduce mutations and stuff like that. And there's people who actually think that that's going to be a benefit when you can sort of introduce sort of like real quantum level uncertainty as opposed to just pseudo randomness. Weird stuff in there. Manufacturing is an interesting question. If you just sort of ride Moore's law, theoretically, we can stand around and 50 years from now, we'll scale up to the point where we have 10 to the 24th transistors in a device. That's a long time to wait, but even worse is Moore's second law, which says that the cost of a foundry is also growing exponentially. And if you scale that out, by the time we get to this point, building a new foundry to manufacture these chips is going to cost about $25 trillion, which is the gross domestic product of European Union and US combined right now. So that's a huge issue. How are you going to manufacture this thing? And basic things like propagation delay, again, if it takes you a picosecond to go from one cell to another, and you try to go from one end to the other end of a 2D matrix, that's going to take you, it's going to take you a second, 10 to the 12th. Okay, so these are serious details that need to be addressed if you're actually going to make this feasible. And the way to address that is to change topics for a while and talk about philosophy.